If you don't have answer, do not worry. So it's okay. So we add here transistor in order to, we need that current will go only through the LID. So transistor actually current will go from these 5 volt terminals through LID through the transistor to the ground. So actually current will not go through the integrated circuit for these reasons. In previous ones, current actually will go through the integrated circuit, just restrict current from the integrated circuit. That's it. Okay, so let's consider wiring scheme. It's the same as the previous one. But there is one difference. Can you see this difference here? I think in the previous we also had. Yes, it's here. It's not. They're not indicated it, but here you can see. You see that all of the unused pins are. Some unused pins they are all grounded. It is needed in order to remove some static charge, because some static charge can damage the integrated circuit. For this reason, the unused pins just grounded. Okay. Next, let's talk about some simple logic gate applications, and then I will show in my multi-slim. Here, actually, it seems very simple, but it is very, useful thing. For example, you can actually calculate the frequency of clock signal. So here you can see clock signal, and it is an AND gate, and will use, for example, it's A input as a control, and B input just just input when we can send this clock signal. So here you can see that when the control A will be high, it means that this clock signal will go through the AND gate, and in the output we will generate the same clock signal, right? But we'll apply low to the AND gate. So on the output it will not, transfer this clock signal. So it's very simple, but it's very powerful. For example, you can hear actually you can calculate. For example, you can for example, in A, you can send just 1 second pulse, and during this 1 second pulse, this signal will go through the B. And here you just by oscilloscope you can count 1, 2, 3, 4, 5. So, but the duration was 1 second, and the frequency will be 5 hertz. So actually, by just this simple AND gate, you can actually calculate frequency of some signal. So it's very useful, simple device. Okay, so let's consider other kind of simple logic gate application. For example, we already assembled these ones. Do you remember?
Yes.
In the last work. So actually, it's count number of signals, right? It's just counter. So actually, here, for example, inverter can be used just to clear the reading here. For example, if you can see that to activate clear, we need to apply low input. So when this switch button, this push button, when it is open, it means that here we have high, here we have 0. But when you push, actually this point is connected to the ground, and here will be 0, and here it is inverter, and here will be 1. And it will activate the clear function and clear the data. Okay, so this one, what do you think? What can be? Do you have some idea what this can be? Actually, here you can see some alarm. That it means it's just some simple alarm circuit. For example, it can be, for example, it can be switch on your car doors. For example, you know, car have four doors, right? And you can just, I don't know how you will do it, but you can, you know, somehow connect some switches to the doors. And here, for example, when you will open the door, for example, this switch will be closed, and we will apply to the input. What is?
Or a NOR.
It's NOR, and we'll apply to its what's high, and output what will be?
Low.
Output will be low, but what is this one's? It's sort of, it's alternative symbol. It's a little bit complicated, but you can see in the book more simple ones without this additional. But the I think in the lab work you should assemble these ones. I will check. So actually, when one of the this switch is activated, alarm will be alarm will start and will indicate that somebody opened the door of your car. So just simple. Of course, in the real, you know, car alarm circuit, it's not so simple. It's more complicated, but it is the base of the alarm circuit design. Okay, so let's do some summary. Then let's go through the labs that we will do tomorrow, and maybe if we will have time, I will show you some circuits that from this lecture, and maybe if we will have time, some circuits that we'll assemble tomorrow. So first, after this lecture and after the reading the chapter 3 of the course book, so you should know that binary logic gates are the basic building blocks for all digital circuits. So actually we have AND, OR, the NOT inverter, NOR, NAND, and XNOR, that other you can just see in the book. The following table shows a summary of the 7 basic logic gates. This information should be memorized. So it is in the next slide, so you will see in the next slide. Okay, NAND gates are widely employed and can be used to make other logic gates. So now you know that NAND gates is more popular, and you should know why, because from the NAND gates you can actually assemble other types of gates. Logic gates are often needed with the 2 to 10 inputs. So several gates may be connected in proper manner to get more inputs. So I show you, for example, how you can get a 4 input AND gate by using 3 AND gate with 2 inputs, for example. AND, OR, NAND, and NOR gates can be converted back and forth by using inverters. So refer to the figure 347 in the textbook, and also you can see in these slides. Okay, logic symbols sometimes have small bubbles attached. So these bubbles usually indicate that these pins are active low inputs or outputs. Okay, so the tables that mentioned in this here in the 2. Yeah? So let's go briefly. So it is an AND function, and it is its symbol. It's a Boolean expression. You should understand that we put some dot N and B equals Y. So it's just truth table for some simple 2 input AND gate. So this is OR gate. OR function, it's symbol. So just notice the difference. Please try to memorize. So for Boolean expression, to show that A and A ORed with B, we use this plus symbol, but it's not plus in meaning, right? So A or B equals Y. So here you can see the truth table. Okay, in the end, interesting this last line. Here, interesting this last line, first line. Okay, here it is inverter, so it's a symbol of the inverter that we will see on the circuit. So its function is very simple. If input will be 0, output will be 1. If input will be 1, output will be 0. So to show Boolean expression, we just use over bar, but sometimes we use apostrophe. Okay, so its truth table is, far more simple, right? So we have just one input, that's it. NAND, so it's similar to the AND, but here we add a bubble. It means that we invert the AND and we get NAND. So it's Boolean expression. So you can see that A and B, and we have this long over bar. If you will write A small over bar and B with small over bar, it's not will be NAND. So to show NAND, you need to write A and B, then show this long over bar is equal to, but you will read how? You will read A and B not, or just not A and B equals Y. So it is the truth table. So next one, it's NOR. It's not or. So it is simple. Actually, it's similar, but here we have bubble. So it's a Boolean expression. Also notice that first A or B, then this long over bar, it means it's inverted, equals Y. So it's a truth table. Next, it's we'll call it XOR. Here it's similar with the OR, this NOR, but here we add some curved line. So it is a Boolean expression, A XORed with B equals Y. So it's the same plus we can see, but it is in a circle. It is truth table. Okay, so here you should understand that this logic simple, it's it's look at the not just inputs. Of course, it's looks at the inputs but it's count high inputs, right? If number of high inputs it's odd, in this case it will give us output 1 high. Okay, so it's a XNOR. So actually it is the same one, but the output is inverted. So the symbol is the same, but with a bubble. So here you can see the Boolean expression, and it is a truth table. So I think with this we've done. And if you have some questions about some slides, you can ask. And then let's me share with you tomorrow's lab works, and let's discuss it. And then I will show you in Multislim some simulations. So guys, do you have some questions about today's lecture? So step by step, our lecture will be becoming a little bit difficult. So please do not miss some chapter, because every chapter depends on the previous chapter. So you need to read. Okay, if you don't have questions, let me. Still, can you see my screen?
Yes.
Okay. So I already uploaded on the Moodle the assignment for tomorrow's lab. Guys, I need to drink a little bit water. So first experiment, it's lab experiment and AND gate. So here it's very simple. So you need to actually assemble this circuit on the Multislim. then this one. So here we have 2 inputs, here we have 3 inputs. So just maybe 4 inputs, I don't know. So read carefully, review this, and tomorrow we will do, okay? So here we have actually, you need to fill up these tables. So you will assemble, check. So we have 2 inputs, right? And what will be our outputs? So here, okay, so we need to you need to review. So next one, it will be OR gates. So actually simple ones, two inputs, more complicated one. Yes, it is how much? 1, 5. 5, okay. So here you see some truth tables. Some maybe should be fill up. Okay, next one. Let's check. Inverters. Okay, so it's just simple ones. So please guys review, but I want to show you other NAND and NOR gates. Okay, so this maybe will be a little bit difficult than previous 3 ones. So here you need to use NAND and NOR gates. So this is simple. It's also simple. XOR and XNOR gates. Yes, but one should be difficult, so let's me using the NAND gate. Okay, here in this experiment, you will use NAND gate in order to perform some other functions. Right? Design what? This one, design problem gates with more than 2 inputs. So these ones maybe take more time to accomplish, but here actually we will not have ready circuit. So you just will have some circuits, and you need to think and come up how can you design, for example, this. What is?
Three and
Yes, this 4 with 4, it's NAND with 5. So this, but also in the multi-slim, actually we will have you will have ready, this kind of ready NAND with these 5 inputs. I think that's design problem converting gates to other logic functions. Okay, these two last two maybe more difficult than previous ones. So guys, before we will come to the lab, read carefully, but if you have some questions, of course, tomorrow I will answer. Okay, now we still have time. Let me show you some simulations. Okay, open. Not here. Lecture 3. Okay, maybe I will show you this one. So this actually, it was from this slide, right? So it's just for simple alarm circuit. So here you can see that actually it's the same, but what different between this one and that I've assembled? Can you see the difference? In this they show 4 input NAND gate, right? Or NOR gate, 4 input. So here I just use actually 3 OR gate and created 4 input OR gate. Then I used inverter. So actually this is my part. This is my part. This. It's actually this one. And also I did not use this additional switch because it's just switch off your alarm. So let's simulate and see what it will produce. I hope it will be working because I've tried. And so now your doors of your car are closed, and for example someone tried to open it. Can you see? Can you hear? Guys, can you hear?
Yes.
Okay, so when I will push, just watch to this reading. So actually it is probe. So for example, I put here what we have, 1, right? But it is OR gate. Up till now it is OR gate. So when I put here we also have 1, but after it will be inverted. Here now you can see it's 1. So when I push, here you can see 0. Then I use buffer. What do you think? Why I'm using buffer? Do you have some idea? Do not worry if you're wrong. Just you can just guess why.
Decrease.
What?
Signal decrease.
Because here I'm using some how can I say in English? This audio, yes, audio systems that produce sound. Yes, sometimes in order to, in a real car, it will take a lot of current. So actually, this inverter cannot support so much current. For this reason, we need buffer. Buffer just give us additional current, additional power. For this reason, so you can see when this high, this also high. So the polarity is the same, and current will not go through the this. I don't know. I forget how in English will be this audio, producing system. But when I will push, it is grounded actually. It is grounded, and current will go. So for example, if I push this one, the same. This one, the same. So actually it's some, simple but real application. How can you produce, for example, design in this multi-slim allow you actually design some circuits that will perform some, real function in real life. Then after you will check that it is working in the multi-slim or maybe in other simulator, then I actually can assemble a real digital system. Okay.
Teacher,
Yes.
can you repeat again why we use buffer?
Okay, guys. For example, LID. It's our so output. This output we connect for some devices. For example, LID or maybe others that will consume current, right? In order to work, it will consume current. But for example, this inverter, it does not give us enough current. For this reason, we use buffer. Buffer is just additional device that just support current. It's just power.
Okay. Thanks.
Okay. So guys, do you have questions about this circuit, about Tomorrow's labs? So I will also today check some works, so review, and tomorrow we will see. Maybe we will not do all of them. Tomorrow I'll give some detail, but last two should be done. last two. This one, because they're more complicated than previous one. So 3-8 and what next? This 3-7 should be done, but I will check what is not necessary from this first parts. So I guess for today we've done, and if you have some question, please ask and I will try to answer.